Okay, let me welcome you to this lecture on infinite horizon problems. We discussed them in lecture 2 to some extent, and today we're going to deal with them in greater detail. So here's the outline. We're going to start with the formulation of infinite horizon problems, and we are going to switch to a different notation, which is more suitable for the type of finite state problems that we are going to be discussing today. This notation will involve transition probabilities. And then we're going to overview the theory of infinite horizon problems and the algorithms. We are going to talk about two types of problems with finite number of states: discounted problems and stochastic shortest path problems. We described them in lecture 2 as well, and we're going to continue to work with these problems. The stochastic shortest path problems, or SSP as we're going to call them, have a little bit more complication than the discounted problems. So we're going to elaborate on them a little bit and describe some of the difficulties of dealing with them, and also with extended versions and other more sophisticated problems. Then we're going to talk about algorithms, and potentially with approximations. Value iteration and policy iteration are the two basic algorithms, and we're going to deal with them and also the approximate versions of them. So value iteration, policy iteration is exact form, approximate policy iteration. Rollout is part of approximate policy iteration. It's just a single iteration of the policy iteration algorithm. And then we're going to discuss some error bounds that provide some guidance as to how we should be operating these methods. So you've seen this slide before. This describes the infinite horizon problem. It involves an infinite number of stages, an infinite horizon, transitions from x0 all the way to infinity, a system equation that determines the transition from a state x to a state xk plus 1. The transition mechanism does not depend on k. The problem is stationary. It involves a stationary system. And x is as usual, x is the state. U is the control. W is a random disturbance whose probability distribution depends on x and u. We're going to be looking at stationary policies that do not depend on the time index. In other words, all the control functions of the policy are the same, regardless of the stage we're in. There are constraints that are again stationary, and the cost of a transition is as before, but there's also discounting. Alpha is a discount factor, which is a positive number between 0 and 1. It could be 1. And this is the cost of the k stage. And the cost of a policy mu is obtained by taking the n stage cost, the finite horizon cost, and taking their limit as n goes to infinity. This is a number that corresponds to the initial state, and it corresponds to the policy through mu. Of course, all of this is random. The expectation here is with respect to the uncertain quantities, the WKs, and so on, as before. And that's the definition of a stationary policy mu. And this is the definition of the cost of the stationary policy mu. It's a cost function, like the ones we have been dealing with so far. And the optimal cost function is obtained by minimizing over all policies for any given initial state. Now back to alpha is the discount factor. If alpha is strictly less than 1, then the problem is called discounted. Now for discounted problems, the cost far into the future diminishes geometrically with alpha to the k, and that's what keeps also this cost finite. The limit exists, and this is a real number, at least for the problems that we're going to be discussing. Now, when alpha is equal to 1, there's no discounting, and the cost can accumulate. So in order to keep this cost finite, it is necessary to have some special state, a termination state, where the system can park, can go there and stay with no cost. That will keep the cost finite. So usually when alpha is equal to 1, there must be, as a practical matter, a cost-free termination state, T. We're going to be denoting by T as before. And this is the general class of problems which are called stochastic shortest path problems, or SSP problems. Now, if there are no stochastics, Wk is a deterministic quantity, then this becomes like a deterministic shortest path problem that you learn about in the first course in algorithms, one of the most basic problems in optimization. So deterministic shortest path problems are a special case of this and provide some guidance as to what we can expect for their more difficult stochastic versions. And these are the two problems that we're going to be talking about: stochastic discounted problems and stochastic shortest path problems. And moreover, we're going to focus on a finite number of states and finite number of controls. This simplifies the analysis a great deal. And it also necessitates a new notation. Okay, we talked about the problem of notation. The notation that we have been using is suitable for deterministic problems and also for problems involving infinite state and control spaces, like in MPC, for example. However, if the number of states is finite, then, and it's also a stochastic problem, then it's better to have the transition probability notation, which I will now explain. Here, and for the rest of the talk, we're going to be assuming that the number of states is n, and we label them by 1 through n. And the successor states are denoted by y. So the transitions are from x to y. And okay, so for SSP, there's also the x determination state t in addition to these n states. And we are going to consider transition probabilities from x to y under control u. These are denoted like so. This is the probability when we are in x and we apply u, the probability that we're going to end up in y. So the summation over y here is equal to 1. In the case of stochastic shortest path problems, there's transition probability to the termination state, of course, right? And also the cost from one state to the next state, the cost of this transition under control u is denoted like so. And now you'll notice a similarity that we have here with our standard notation up to now. The two notational systems are equivalent, mathematically equivalent, functionally equivalent, but more convenient for some problems. One system of notation is more convenient for some types of problems, but not for others. And the mnemonic here, to go from one notation to the other, is to think in the new notation as this being the new system. All the uncertainty is encoded in Wk through its this probability distribution. So in the new system, we replace this transition equation with this type of transition equation. And we replace the distribution of W given X and U with the transition probability. Okay, Y is equal to W. This is the conditional distribution that we end up in Y, given that we start in X and we use U. So in the new notation, we have a simpler system and a three-dimensional matrix here, which is more complicated description, I think, than the one for the distribution notation. Now, given this insight here, how do we pass from formulas in one notational system to the other notational system? Well, the expected cost per stage that we had before in our formulas is replaced by this expression, the expected cost of the state, the expected cost of the transition, starting at u and starting at x and using u as our control. The probability of going to y is this one, and it weighs the cost of going to y. So this is the correspondence. And similarly, expected cost to goes in the previous notation system are replaced by this one, expected value of the cost of the next state, given that we start at x and we use control u. So with this mnemonics, Bellman's equation for discounted problems in the new notational system looks like so. This is a system of equations for the optimal cost values. J star is a vector now of n values. Remember that n states here. So these are n equations with n unknowns, the values j stars of 1, j stars of 2, up to j stars of n. And look at this expression here. It involves minimization of the first stage cost plus the discounted optimal cost to go from the next state y. Okay. So we're going to be looking at this expression a lot. This is Bellman's equation for discounted problems. And for stochastic shortest path problems, a similar equation, but we have to take into account the termination state. There is also part of the expected cost is the portion that deals with the termination state. So this is the conditional expected first stage cost, conditioned on the fact that we go to the termination state. And this is the conditional expected cost, conditioned on the fact that we don't go to the termination state. So this is overall the first stage cost. This is the optimal cost to go, and it's the usual minimization here. And it is again n equations with n unknowns, the j stars of the states. So this is what this is how our notation is going to look like. I'm sorry about the confusion, but in my opinion, there's no way to avoid using two different notational systems, because this notational system is good for stochastic problems with a finite number of states, but it is absolutely horrible for problems with infinite state and control spaces, and particularly deterministic problems. It just simply doesn't make sense to put all of your description in one basket, okay, these transition probabilities, when there's no uncertainty in the problem. So this is the best notational choice that I can come up with. And I don't think it's very difficult to get used to it, and these mnemonic conventions will help you in this regard. Are there any questions? Okay, so now let's summarize the theory and the algorithms and preview what we can expect to see. Remember from lecture 2, the 3 theorems of infinite horizon dynamic programming. When the problem is discounted with a finite number of states, or more generally, if the cost per stage is bounded, okay? This is true certainly if the number of states is finite and controls is finite. Now, in this case here, the entire exact theory goes through with no exceptions. I mentioned that we expect these 3 theorems to hold, but there are some exceptions. Well, for the case that we're going to consider here, the discounted case with a finite number of states, there are no exceptions. Everything works out very nicely. This is the nicest problem of stochastic infinite horizon dynamic programming. Now, what are the 3 theorems? The first theorem deals with convergence of the value iteration algorithm. The value iteration algorithm computes sequentially the optimal finite horizon costs with larger and larger horizon. Jk sub x is the optimal cost of the k stage problem with terminal cost approximation J0. And it is obtained by cranking the dynamic programming algorithm forward, accounting also for the discount factor. First stage to go, cost to go from the previous, the k stage horizon problem, we obtain the optimal cost to go for the k+1 horizon problem after minimization here. So this is value iteration, a very fundamental algorithm. It's just an infinite stages version of the dynamic programming algorithm that we know and love. Okay, Bellman's equation. This is the equation, and the theory says that you can expect that J star solves this Bellman's equation. And in the case of discounted problems, this is the unique solution. J star is the unique solution of this Bellman equation. So that's a nice thing. And the third theorem says that if you minimize in this expression here of the Bellman equation with J star here, then you obtain an optimal policy. Moreover, if you have an optimal policy, then it must attain the minimum here. This is an if and only if statement. So these are the three theorems. You expect them to be true. They're not always true, but in this particular case, they are true. Moreover, there is another Bellman equation that's focused on a single policy, a given policy mu. It takes this form here. We simply take away the minimization. There is only one policy and substitute mu sub x in place of u here. And this is an equation that is solved uniquely by the cost vector of J mu, of the policy mu. Now, the difference between this equation and that equation is that this one is linear. It's linear in the variables J mu. And whereas this one is nonlinear because of the minimization operation here. So this can be solved by MATLAB, by Gaussian elimination, any one of your favorite linear algebra methods. On the other hand, remember that we are interested in problems where the number of states is potentially huge, in which case the MATLAB algorithms go out the window, okay? You have to use some other kind of method to solve this equation approximately, either by iteration, possibly by value iteration actually, or by some other method, simulation as you need them, and so on. So this is the theory for discounted problems and the value iteration algorithm. And the other major algorithm is policy iteration, which we have covered in one way or another, and today we're going to look at in more detail. It is intimately connected with a rollout operation. It generates a sequence of policies, and at the typical iteration, we have a base policy. We evaluate it by solving the corresponding, by getting the J mu values that we need, and then we do a policy improvement operation, which is minimization in the Bellman equation, but with J mu in place of J star. We can compute far more easily J mu than J star. That's why we prefer to minimize in Bellman's equation with J mu. Now, this policy improvement gives us the rollout policy, and if we make this the base policy for another iteration again, we can loop infinitely around this loop, generate a sequence of policies. And the important fact is that for the problems that we're going to be discussing, and generally we expect that policy iteration yields in the limit an optimal policy. For discounted problems with a finite number of states, it will actually terminate in a finite number of iterations. It will find an optimal policy in a finite number of iterations in its exact form, of course. Now, you have policy iteration and value iteration. Value iteration is a little cheaper it's quite a bit cheaper to implement than policy iteration, but policy iteration is much faster. It is connected to Newton's method for solving Bellman's equation, as we have explained in lecture 2. It's a very important insight, both for rollout, because rollout is a single iteration of Newton's method, and also for the speed of convergence of policy iteration. And so policy iteration, if you can implement it, if you can have it, is much faster. And if it's exact, it gives you the optimal policy. However, in reinforcement learning, we have to deal with approximations because the problems we're looking at are very challenging. And very often we have to resort to simulation, typically around the policy evaluation step. There are a number of simulation methods, and we have discussed simply averaging samples of state and cost pairs to calculate the values of J nu that we need by Monte Carlo simulation. But there are also other algorithms, and a lot of the reinforcement learning theory deals with these algorithms. There is a nice mathematical algorithms with intricate analysis and sophisticated properties. And one class of methods which played an important historical role, but we're not going to cover it in this course, is the class of temporal difference methods, TD methods. You'll see a lot of literature about them. These TD methods provide an alternative method, an alternative possibility for doing this policy evaluation, either exactly or approximately using simulation. Okay, now when it comes to approximate implementation, we have discussed also value and policy networks and their training using data, cost, state and cost data to train neural networks to approximate target functions, which are this J nu, and policy networks that use state control data to approximate target functions that are policies. And we noted also that these policy networks can be viewed also as classifiers, so they can benefit from software and algorithms that are known in classification theory. So approximate policy iteration operates like exact policy iteration, except we use value data to train a value network here, and policy data to train a policy network here. And then we obtain an approximate rollout policy, and we may stop here if we want to do just approximate rollout, or we can go into a loop and generate multiple base policies and corresponding rollout policies. Now, the important thing to remember is that the first iteration of this loop can be used for approximation in value space. Online play, okay, for controlling the system in real time. Rollout is a one-time play online play type of algorithm that does not need to have a policy network or a value network. Once you go into multiple rounds of iterations, then there is no alternative but to have a value network or a policy network or both of them. Okay. Now, having to train a neural network or other approximation architecture with data means offline training. You can't use this type of algorithm online. You have to train offline and use the last policy that you get in an approximation value space scheme for online play. So we have covered the three theorems and the two algorithms of value iteration and policy iteration for discounted problems. Now we're going to go into Stochastic shortest path problems and look at counterparts. Are there any questions? Maybe you guys know all this already.
given all the stuff that we went through. Are there any questions? Okay, so now we're going to go into stochastic shortest path problems with finite spaces, finite states, and finite control, and I'm going to give you the main results. Now, there's an assumption in stochastic shortest path problem that's the most favorable, and this is that termination is inevitable under all policies. By this we mean that there is some number of stages such that for every policy and every initial state, there's positive probability that we are going to reach the termination state within the first M stages. Now, M may be 1, maybe 10, maybe 100, maybe 1,000,000, but there is a number such that the termination state is reachable with positive probability for every policy and every initial state. That's what this assumption says. Okay. So basically, this assumption says that this is really a finite horizon problem, except that we don't know when we're going to terminate. We're going to terminate eventually with probability 1, but we just don't know when we're going to terminate. Moreover, every M stages, the probability of having terminated increases. So after a lot of stages, the probability that we have not terminated is negligible. So this is really a finite horizon problem, and this also manifests itself in the line of proofs, the mathematical proofs that you use under this assumption. The analysis is relatively easy, and the results that you get are the 3 theorems with no exceptions other than this assumption. Value iteration converges for all initial conditions. And note now that the value iteration involves the additional expected cost to reach the termination state from the conditional cost of reaching the termination state from X under control U. Bellman's equation similarly involves that cost, and J star solves this equation and is a unique solution of this equation, and the optimality condition is that mu is optimal if and only if mu attains the minimum in this expression. So everything goes through under this assumption, and moreover, the analysis is easy enough to be the basis for the analysis for discounted problems. Here's the line of analysis. The idea is that SSP are easy to analyze, easy to understand, and discounted problems may be a little bit, but discounted problems can actually be transformed into SSP problems. There's a certain equivalence, so that we first analyze SSP, and then the results for the discounted problem fall out for free. So that's the point here. A discounted problem can be converted to an SSP problem with termination inevitable, so that the theory of the preceding slide applies. Okay, so this is our original discounted problem. This is the Markov chain corresponding to U, the transition probabilities between the different states. And when we are at X and we apply U, this is the expected cost per stage, except for the discount factor. Now we're going to formulate this stochastic shortest path problem, where we introduce an artificial termination state T, and at every stage, for every state, there's a probability 1 minus alpha. Alpha is less than 1, so this is a positive probability of going to T from any state. And conditional that we don't go to T, the probabilities of going to the other states are according to the original transition probabilities. So when we are at X, there's a probability of alpha pxy u to go to y, and a 1 minus alpha probability to go to t. And the probabilities add up to 1, of course, as they should. Now, I claim that this stochastic shortest path problem is equivalent to this discounted problem in the sense that the costs of policies are equal in both problems and the optimal policies are the same in both problems. What's the reason for this? Well, what is the cost of the kth stage for the discounted problem? It is this expected cost times alpha to the k. Now, what is the cost of the kth stage in this problem starting from x? It is expected g times the probability that we have not terminated already. But that probability, times the probability that we have not terminated, which is alpha to the k. So the cost of the k stage for the SSP problem, probability we have not terminated, times the regular cost that we would incur at x given u. So the transitions are the same as long as we have not terminated, and the costs are the same as long as we have not terminated. So the two problems are equivalent. They have the same cost. It's easy to see that. And also the same policies because the structure of control is the same within the two. So here how we get proofs for the discounted case. Start with the SSP analysis and get the discounted analysis as a special case. It's immediate almost. Now, this line of proof applies to finite state problems, which are the ones that we are going to consider in this lecture and in this class. On the other hand, if you have a more complicated problem, for example, involving an infinite number of states, still discounted, this line of analysis does not work. The reason is that there is no easy theory for stochastic shortest path problems with an infinite number of states. So the SSP theory is restricted to finite state problems. And therefore, for infinite state problems, you need a different line of analysis. And this involves contraction mapping ideas. The idea that the Bellman equation operator is a contraction mapping from a function space into a function space, the function space of cost functions into the same cost function space. Now, this takes us a notch further along the mathematical ladder, and that's why I have preferred to go along this line here. But this is an important line of analysis. And for those of you who are interested seriously in this field, particularly its mathematical aspects, is something that you should look into. Okay, so now what we're going to do is go into stochastic shortest path problems and weaken the assumptions a little bit and see what may happen after that. Are there any questions so far? Okay, guys, moving right along. So let's go into stochastic shortest path problems and elaborate. Okay, we said that everything is nice when we have this assumption of termination inevitable for all policies. On the other hand, many stochastic and deterministic shortest path problems of interest do not satisfy this assumption. For example, take a deterministic problem that has a graph with a cycle, okay? Then there's a policy that just spins around the cycle and never terminates. So immediately, termination inevitable is violated. And most of the deterministic shortest path problems involve cycles. It's very common to have a graph that involves cycles. So it is very common for this assumption to be violated. Now, we have to replace this assumption with some other assumption, and here's one that is nice. and applies broadly in practice. Okay, this says that non-terminating policies are bad. Yes, there may be some non-terminating policies in this assumption, but they have infinite cost for some initial state. So here's a more precise statement of this assumption. It requires that every policy that does not terminate with positive probability has infinite cost for some initial states. In the context of deterministic shortest path problems with cycles, we require that there is positive cost of going around a cycle, so it's not optimal to spin around. It's the thing to avoid. So this is one part of this assumption. And the second assumption is that there exists at least one policy under which termination is inevitable. This is necessary to keep the cost finite, among other things. So it is always possible to reach the destination with probability 1. That's what it says. However, there are some policies that don't do that, but these policies are bad and they have infinite cost for some initial states. So this is the assumption, and it's a reasonably substantial extension of the theory, and it requires some sophistication in its analysis. It requires, you'll see a theory revolving around proper policies and improper policies, and we're not going to go into the details here, but the major results, the three theorems, are salvaged under this assumption. That's the important thing for us. On the other hand, if you try to go beyond this assumption here, things can get very hairy. Very unusual things can happen, and the theory is still evolving, particularly in its approximate versions. Okay, things that can happen. Bellman's equation can have many solutions, not just one, but many. Another one that's kind of mind-blowing, Bellman's equation may have a unique solution, but that solution is not equal to J star, okay? That blew my mind when I found out about it because it seems so unlikely. But it is true for stochastic problems, not for deterministic problems, but it can happen for stochastic problems with relatively few states. Now, once you have this kind of anomalies, then value iteration and policy iteration may fail, even for finite state problems. Infinite state problems can become very strange behavior. All of this and more, even with bounded costs per stage. And all of this is a mathematician's delight, okay? Interesting proofs, interesting phenomena, a lot of insight the mathematics reveal a lot of insight into the structure of the problem, but it's beyond our scope in this course. But my online abstract dynamic programming book deals precisely with all these issues, and the mathematicians or aspiring mathematicians among you may consult it for further material. Okay, so now let's take an early break. I'll take a 15-minute break, and that will give you a chance to think about some challenge questions. Here is a tricky stochastic shortest path problem, actually deterministic problem. And it's the simplest deterministic problem that you'll ever find. One of the simplest problems in optimization, actually. Here's the problem. You have one state plus the terminal state, and you have two actions. This action keeps you in the same state and costs A. This action leads you to the terminal state and costs B. So there's only one decision to make. as far as stationary policies are concerned, and it fits our framework, right? A finite number of states, a termination state, deterministic transitions, and given costs. So there's a Bellman equation associated with it, and all the other stuff. On the other hand, consider the case where A, this cost here is 0, okay? So spinning around a cycle costs you nothing. Then it may be optimal to just spin around the cycle, right? Particularly if B is positive, that would be the only optimal policy. So let's look at, the other thing is that this policy here violates the non-terminating policy are bad assumption. Why? This is a non-terminating policy, but it has cost 0 if A is equal to 0. So it doesn't have cost infinity from the one initial state that we have here. Okay, so this example violates our assumption. And here's Bellman equation, right? Bellman's equation is a one equation with one unknown. Why? Because there's only one state. And this unknown is J's of 1, okay? And it involves, the right-hand side involves minimization between the cost of control of this control, which is B, and the cost of this control, which is A, plus J's of 1, okay? The cost to go from the state where you land. Okay, now Bellman's equation has multiple solutions. And the reason is explained here. This figure here shows you Bellman's equation. This is the right-hand side of Bellman's equation, okay? And this is the left-hand side of Bellman's equation. So this equation has multiple solutions. And you can easily see also that the value iteration algorithm converges to J star. J star is equal to A here, right? Because A is if B is positive, then it's equal to A. If B is negative, then it is B. Okay. And it's evident, however, from this figure that the value iteration converges to J star from some initial condition, but not from others. Now, what I want you to do in this 15 minutes is to verify the statements here, assimilate the character of this figure and the problem, and consider the cases where A is positive, A is 0, and A is negative. What's happening in these three cases? What assumptions are satisfied, and what's going on with Bellman's equation? What's going on with value iteration? What is J star? What's the solution set of Bellman's equation? One solution, multiple solutions, no solutions? What is the limit of the value iteration algorithm? Okay, this is the value iteration algorithm, right? It iterates with this mapping here. And what does it do? Does it converge to something or not? So are there any questions here? Guys, is this clear?
Yes.
Okay, good. Thank you. So let's meet at in 15 minutes at 5:35 Arizona time. Okay? Okay. Okay, so what we want to do now is look at this simple problem with one state and the two controls. And we want to examine the three different cases where A is positive, 0, or negative. And what happens with Bellman's equation? What kind of solution does he have? And
about the value iteration algorithm starting from an arbitrary J0. How does it behave? So what if A is positive? Okay, so who wants to discuss this case? What's the solution of Bellman's equation?
Well, I think it would just converge to B, right? Or the at least value iteration would. It's because you're just adding the future stages A plus J1, but A is positive, so that cost keeps accumulating up to the point where it reaches B.
Yeah. So what is J star?
B.
Starting from 1.
I think it's B. Right.
It's B, right? Because the cost of the other points, for staying there is infinite, right?
Yep.
And now, how about Bellman's equation? Is J star equals B is the unique solution of this equation.
I think so.
Can we tell from this figure or a modification of this figure? Okay, so for A equals A positive, this line here is going to rise up here somewhere, right?
Mm.
So this red curve, which is the right-hand side of Bellman's equation, is going to go like this, right?
Mm.
And the point where the two of them intercept, the left-hand side of Bellman's equation and the right-hand side of Bellman's equation, intersect at this point here. So this is B, right?
Yep.
And is there any other solution? Are there any other points of intersection?
No.
There are none, so this has a unique solution. And how can we explain this with theory? Well, it is part of the second theorem, right? The Bellman's equation has a unique solution under the assumption that non-terminating policies are bad, okay? We have our assumptions holding for this case. The cycle has positive cost. The cost of staying within the cycle is infinite. So this non-terminating policy is bad. And we have a unique solution. How about, okay, value iteration converges to B. You can see that, okay? If you have, if you are anywhere, then you take the minimum of B and this, it's the same. So it's going to go to B after one iteration, I believe, starting from this side, and it's going to take, I think, yeah, something similar from other initial conditions. So everything works fine. We are in theory in this case. Now, what happens when A has A is equal to 0? Who wants to discuss that? What is Bellman's equation in this case? Well, A is equal to 0. So this line here is going to go up to here. And the right-hand side of Bellman's equation is going to be this. And it intercepts the left-hand side, which is this, along this line here. So all the numbers from B going lower are solutions of Bellman's equation. There's an infinite number of solutions. The minimum between 0 and B is J star, okay? And you can, okay, for first principles, it follows. Bellman's equation for A equals 0 is this one, and the solution set is from B to minus, from B to minus infinity. Now, the value iteration algorithm has this form, okay? A is equal to 0. It converges to B starting from higher values. You can see that from, okay, in a number of ways. But does it have a unique limit? Suppose we start at a different starting point. Suppose that we take as a starting point any one of these solutions here, okay? Then all of the solutions of Bellman's equation are fixed points of this iteration. This iteration is not going to move if it starts at one of its solutions. So the value iteration algorithm will converge to B only if it started from initial conditions higher than B, but it will not move from a starting value less than B. And the most strange case happens when A is negative. Anyone wants to discuss this? A negative is shown here in this figure. This is the right-hand side of Bellman's equation, and this is the left-hand side. They don't meet at all. There's no solution to Bellman's equation. All of the assumptions, of course, that we have are violated. Non-terminating policies are bad. In fact, the non-terminating policy is optimal here. And the optimal cost is minus infinity. And okay, strangely, value iteration diverges to this minus infinity. But this is, of course, outside our theory, because in our framework, all policies must have, okay, this cannot happen. J star should be, Bellman's equation is an equation in real numbers. Okay, now, I know that this is a very strange example, but it's also a very revealing example. And I want to ask you as a homework to go through this example in detail. It's actually very simple to do that, and it's very revealing, and may also dispel some of the preconceptions that you may have about the nature of our results in dynamic programming and reinforcement learning. In more complicated stochastic shortest path problems involving infinite state space, involving these cycles and so on, if you try to use a reinforcement learning algorithm on that type of problem, it's going to go crazy, okay? It's not going to do anything, and you're going to be scratching your head as to what's happening. But what's happening can also be understood in terms of this simple example here, which is thus very suitable for sharpening your understanding and into what we are doing. Okay, so let's go right along. Let's go into algorithms some more, in particular, an approximate version of value iteration. Now, we have discussed in the previous lecture an approximate version of the dynamic programming algorithm, the so-called fitted value iteration, and we're going to discuss the same algorithm in the context of infinite horizon problems. And this is fitted value iteration. Now, the exact value iteration algorithm for the discounted problem, we're going to focus on the discounted problem from now on for the most part. The value iteration algorithm is given by this equation. From J0, which is arbitrary, it generates J1, and then J2, and so on. And each time it applies a dynamic programming operation. Each time it finds the optimal cost of a finite horizon problem with length of horizon one more than what it was before. Now, how can we do approximations of this algorithm? Well, what we can do is do this minimization approximately and then call the result the new iterate. So we start from J tilde 0, then generate J1 tilde by minimizing here within some delta, okay? So this minimization is exact within some delta, and delta is the maximum tolerance over all states. And then we go to J2, again making an error, an approximation error of delta, and go forward.
This is exactly the same kind of algorithm that we discussed with neural network approximations encoding these J tildes. In fact, one of you asked the question, do these errors accumulate? Well, in a finite horizon context, they accumulate a finite number of times. But in an infinite horizon context, they do accumulate. And now I'm going to give you an example of how they can accumulate. Okay, first of all, a theoretical result, a fake theoretical result. If you assume this condition, then you can prove that the error, the long-term error between the iterates of this fitted value iteration and the optimal cost is bounded by delta over 1 minus alpha. It's a positive number proportional to delta. So this result says that if this condition holds, then the long-term error that you will incur over an infinite horizon is delta over 1 minus alpha. On the other hand, this result assumes that this is true. In other words, assumes that you can minimize within delta. And strangely enough, this may not be possible when errors accumulate. So this result may not be meaningful for some natural methods because it may be difficult to maintain this equation over an infinite horizon because errors accumulate and the J tilde sequence may become unbounded. So let's give a simple illustration of that, one of the classical examples of reinforcement learning and approximate dynamic programming. We start with some J tilde 0, and we let J tilde k be generated by using some parametric architecture. We'll give an example of that. And given the parametric architecture, we obtain a parametric approximation, J tilde k, using a least squares fit, the natural thing that you would do. And we'll show how the cost function error can accumulate to infinity. We're talking about fitted value iteration and approximations, and here's the example I want to give you. It's an old example, and it deals with the instability of fitted value iteration. Now, this is also a very, very simple discounted cost example. It involves a single policy and two states, 1 and 2. And that policy moves from 1 to 2 deterministically and stays at 2 deterministically, in both cases with cost 0. So the Bellman equation has this form. One stage cost is 0 here, right? And what's the unique solution? Well, it's the optimal cost function. The optimal cost function is the 0 function here, right? Because the cost is 0. And what is the value iteration algorithm? Okay, the value iteration algorithm has this form, okay? Jk plus 1 of 1 is 0 plus alpha jk of 2, okay? Now at state 2, value iteration gives you 0 plus alpha jk of 2 because you stay at 2, okay? jk's of 2 is on both sides of this, on the right side of both of these equations, right? And start given any initial condition, value iteration converges to 0. Alpha is less than 1, right? So whatever you started with is being reduced by a factor alpha each time, and it converges to 0. So now, suppose that we introduce approximations in this value iteration, and we approximate the value iterates within some subspace. And this is the approximation subspace. Okay. Now, okay, so let's get oriented a little bit here in this figure. This is another one of your homework exercises to understand this figure. I think there's a lot of benefit in understanding it, and you can do that. But in the short time that I'm going to explain it, you might have difficulty figuring it out right away. But I want you to try to understand it. Okay, so here is there are two states, right? 1 and 2. So this is J1 and this is J2. And the optimal cost vector is 0, right? And let's consider value iteration and then approximating the iterates on this subspace. In other words, here, this corresponds to an approximation architecture that involves a single parameter, R. And this parameter and this architecture is defined by weights, 1 and 2, okay? And it's this line here. So we approximate a two-dimensional cost function, two states, on a one-dimensional subspace. That's what this approximation will do. So now what we want to do is take an iterate of fitted value iteration on this line, which has to be of the form, it should be aligned with a vector 1, 2, and apply the value iteration algorithm to it, which will give us this vector here, okay? Now the value iteration algorithm multiplies by alpha, the second component. The second component of this vector is 2rk. So it's multiplied by alpha to get both of the components. That's value iteration starting from this point here. Gives you this. And now what do? We approximate this on this approximation subspace. So we fit it by projection. That's least squares approximation, right? So starting from here, we do an exact value iterate and we do an approximation by projection on this line here, and we get J tilde K plus 1. But now what I started and what I ended up with are going further along this line in that direction rather than in that direction. In other words, from here, I don't get any closer to where I want to go, but I get further away. And if I do the same thing from this point, I'm going to get an exact value iterate, projected back again, and then I'm going to get an even further away iterate, and so on. And the iterates diverge of value iteration, and the errors to J star, of course, accumulate over time. And the assumption that I made in the previous slide is also violated. Okay, are there any questions about this and how the algorithm fails? Okay, how can we fix the algorithm? Now, this is a serious research issue in reinforcement learning. People have spent a lot of time trying to figure out how to make these approximations so that this instability does not work. This instability does not occur. Okay, here we have used orthogonal projection on the approximation subspace, but it is also possible to use a different kind of projection with a weighted projection that has that doesn't go at a 90-degree angle onto the subspace, but rather it goes somewhere else. It goes like that. It's an oblique projection. And the kind of projections that you can use are from here to here. This is the one extreme where you weigh one coordinate and the other one is 0. And here's where you weigh the other coordinate in the projection. And those projections, the ones that map below this point here, work, give you convergence. And those projections that correspond to weighting in an opposite way, the two components, do not converge. So, okay, now how can we control these weights of the projection? Well, the weights of the projection are actually related with sampling rates. How often do you sample when you do things, approximations with neural networks and least squares fit and so on, using more samples of one component versus using more samples of the other component, you can control this. The character, the weighting of this projection. And if you do the sampling in the right way, then you get convergence of fitted value iteration. If you do it in a different way, you may not get convergence. And people have figured out that these optimal sampling frequencies are related to the optimal, the long-term occurrences of the different states, the significance of the different states under an optimal policy. Okay, now this is a lot of theory that I'm cramming into these simple statements, but I want to make you aware that this is a significant question that has been researched. It places fitted value iteration into doubt, particularly when you compare it to policy iteration, and that all of this can be explained, like many other things in reinforcement learning, can be explained with simple graphical examples. Questions? Okay, so now let's go to policy iteration, which is our main, the workhorse algorithm for this course. We have seen it before. It generates a sequence of policies starting from a certain policy. We evaluate it in some way, and then we generate an improved policy by policy improvement, and we keep going around the loop. There are two phases: policy evaluation. For the current policy in UK, we do a policy evaluation by solving the system of Bellman equations corresponding to that policy. And we do this in a number of ways: simulation in the context of simulation-based Monte Carlo-based rollout, or for simple problems by Gaussian elimination, and so on. This is the theoretical exact version of policy iteration and policy evaluation. And then the policy improvement phase calculates the new policy by minimizing Bellman's equation, but instead of J star, we have J mu K from the previous evaluation. Okay, so we've seen this before. That's the exact form of the algorithm. How does it work? Well, here's the theorem. The exact form of policy iteration generates an improving sequence of policies. In other words, every new policy is better than the preceding policy uniformly for all states, and also the sequence terminates with an optimal policy. The reason being that, okay, once the algorithm generates the same policy or the same cost, it stops. And this theorem says that it will find an optimal policy in a finite number of iterations under our assumptions, which are a discounted problem with a finite number of states. Okay, now I want to outline the proof here, and part of your homework, again, you delivered the last homework last Sunday. Now I'm giving these mini homeworks, which I think, however, are going to be very useful to you to go through, to try to go through and puzzle them out. I'm going to outline the proof of this result. And this result is important. First of all, it's intuitive. By studying the proof, you can understand how the method works. And second, because this is the standard proof, just about every policy iteration convergence proof uses a similar argument, a modified version of the algorithm that I'm going to describe. And this algorithm is based on monotonicity. We're going to construct a sequence of functions that are lower than this J mu, and they converge to J mu tilde being the rollout policy obtained from the base policy. And incidentally, this also gives a proof of cost improvement for rollout, because this applies for every iteration, and also for the first one, which is rollout. So here's the key construction. We have mu, right? and we can generate mu tilde by policy improvement. And let's call Jn the cost function of a policy that applies mu tilde for the first n stages and then applies mu after that for the remaining stages to infinity. Okay? So now we can calculate this Jn, by the way, by value iteration, starting from J mu and going backwards for n stages. So mu satisfies this Bellman equation uniquely. And what is J1? J1 is the cost obtained by applying mu tilde for the first stage and then mu after that. Now I claim that this is less than J mu. J1 is less than J mu uniformly. Why is that? Well, by the policy improvement equation, because mu tilde is obtained by minimizing this expression with mu sub x replaced by u. Therefore, mu tilde, this expression here, for mu tilde is going to be less than this expression here. So it follows from the policy improvement equation that we have a first inequality. And now I'm going to cascade those inequalities going backwards. I'm going to go to J2 and I'm going to prove that it is less than J1 and less than J mu. How so? Well, J2 by definition is the result of applying mu tilde for two stages. So it's the same as applying mu tilde for one stage and then taking J1 as a terminal cost approximation, okay? Because J1 is the result of applying mu tilde for one stage and then applying mu after that. So J2 is equal to that. However, J1 is less than J mu, so I can continue my inequality this way. So I have, this is now equal to J1, right? So J2 is less than J1, which is this, which is less than J mu, as I proved earlier. So I have this relation holding for all x. And I can go backwards. It's really what we call a monotonicity argument, generating a monotone sequence of functions that starts with J mu and goes downward for all n and for all x. On the other hand, Jn, what is Jn? Is the cost function of a policy that applies mu tilde for the first n stages and mu thereafter. So it's the result of value iteration after n steps of value iteration. We know that value iteration for mu tilde converges to J mu tilde. So this sequence of functions is going to convert to J mu tilde. Therefore, J mu tilde is less than J mu. This is the proof of cost improvement that I'm looking for. It uses a value iteration algorithm to generate a monotonically decreasing sequence of functions that converges to J mu tilde. Questions here? Okay, so this is an important proof, perhaps the most important proof around policy iteration, but also it's important additionally because the line of proof applies to just about any kind of policy iteration algorithm. And here's one that we're going to discuss right now, optimistic policy iteration. Now, just as approximate policy iteration or exact policy iteration for a single, the very first iteration is rollout. Optimistic policy iteration consists of truncated rollout. Just as policy iteration consists of repeated rollout, optimistic policy iteration consists of a repeated truncated rollout, whereby the rollout is for a given number of steps and then a terminal cost function approximation is used. Now, optimistic policy iteration is very important in reinforcement learning. It comes in all kinds of algorithms, in all kinds of contexts. And we have seen the context of truncated rollout, but it also, the ideas apply in other contexts as well. So let's see how it operates. Okay, now to do truncated rollout, you need a base policy and you need a terminal cost approximation. So each iteration starts with mu k and jk and generates mu k plus 1 and jk plus 1. Given the typical pair, we do truncated rollout with this base policy and this cost function approximation. How do we do that? Well, we do mk steps of rollout using mu k. We start with the terminal cost approximation and go back several times, iterating with the policy mu k to obtain the cost over mk stages. So start with this, generate mu k's of 1, then mu k's of 2, and so on for all states. So that's the policy evaluation. The policy improvement is standard. Given this result of the policy evaluation, we minimize in the standard policy improvement equation to obtain the new policy. Again, this is exactly what truncated rollout does. One step look ahead plus mk steps of rollout with the given the current base policy plus terminal cost approximation. So this is obtained by policy improvement, and this is the new terminal cost approximation that corresponds to this minimization here. This is optimistic policy iteration, and it's just repeated truncated rollout with this particular scheme for terminal cost approximation. And the convergence of this, a similar convergence result holds for this optimistic version of policy iteration, using essentially the same argument as for the standard policy iteration. Again, we generate a sequence of decreasing functions and using monotonicity arguments, and we prove convergence in a similar way. It's a standard pattern. Okay, here's another type of policy iteration, multi-step policy iteration. It's like the standard version, except that it uses multi-step look ahead for policy improvement rather than one-step look ahead. So given the typical policy, we do the standard policy evaluation, calculate the cost function of that policy by solving the corresponding Bellman's equation. Then we do policy improvement, but with L step look ahead. In other words, we solve the L stage problem with terminal cost function J mu k. And if this is the optimal policy of the problem, we take the first component of this L step policy, and that's our new policy, and we throw away the rest. We have gone through algorithms like that before, and we give it a name. Now we call it multi-step policy iteration. And there is, of course, the easier case of multi-step rollout that we have seen. Now, what's the motivation for this? It's the same old motivation as for multi-step look ahead. We may get better policies with multi-step look ahead rather than with one-step look ahead at the expense of having to go through a more complex policy improvement involving L steps as opposed to one step. Now, the convergence results for this is exactly the same as for standard policy iteration. Convergence in a finite number of iterations to the exact optimal cost function in an optimal policy. And the proof argument is also almost the same as the proof argument I gave you. Now, there are also various combinations of policy iteration algorithms. Optimistic multi-step, okay? And again, it admits a similar convergence analysis. all these different versions of policy iteration, and you can mix and match features, as it turns out.
I have a question here.
Yeah.
So if the convergence is similar, then why multi-step look ahead can give you the better policy?
Okay, the convergence is a mathematical result. All it tells you is that it converges to the exact value. It doesn't tell you how fast it converges, whether one converges faster than the other, whether it gives better policies, okay? All it says that eventually you're going to get the optimal cost function and an optimal policy. That's what this result will tell you. But our motivation is that in the sequence of generated policies, we're going to be getting better policies with multi-step look ahead rather than with one step look ahead.
Okay, thank you.
Okay. One moment, please. Okay, now let's go to approximations. Here's an enriched version of our standard figure that describes all the different variants for policy iteration and for rollout if you do this only one time. There are the three approximations. There's approximation, the minimization, a simplified minimization, and an example of that we have gone through is multi-agent policy improvement. I'm going to discuss that, by the way, in the next lecture as well, where we do an approximation to this minimization operation. Then there's approximation of this expected value. Okay, this involves an expected value here. We may do an approximation using our standard schemes, adaptive simulation, and so on. And then there are the various approximations of the J mu, the cost function of the current policy. And this can involve rollout with possibly inexact simulation, truncated rollout, which is what we call optimistic policy iteration. We can use parallel rollout. We haven't discussed this in the context of policy iteration. We have discussed in the context of rollout, but it is possible. If you maintain multiple policies, then you can use something that's the minimum of the approximations of these multiple policies. And another possibility is through problem approximation, aggregation in particular, that I hope that we will have time to discuss in our last lecture. So there's a broad spectrum of rollout and policy iteration variants, and you can mix and match approximations to get a rich variety of methods that may fit better or worse your own particular problem. Moreover, this is for one-step look ahead. There's also a multi-step look ahead version. The multiple policies version is this one here, uses J tilde as the minimum of several cost function of policies, perhaps with approximations. Okay, you can do this either in one iteration or multiple iterations, and the approximate policy iteration algorithm generates a sequence through repeated approximate rollout. Now, as I mentioned earlier, approximate rollout needs offline training. And either for a policy network to do this rollout, or with a value network to approximate the cost function. And, okay, it may use some of this stuff here. For example, you may use multi-agent policy improvement offline, training offline a neural network. Okay, so now our last topic is error bounds. Here, we do a lot of approximations in the minimization, approximations in the cost function of the base policy, other stuff here. Can we say anything about the limit or the error incurred by these successive policies generated by policy iteration? When you do approximate policy iteration, you generate a sequence of policies, and none of these policies is going to be optimal. They're going to be suboptimal to a certain degree. Can we say something about how suboptimal they're going to be in the limit as you add more and more iterations? So this is an important question, and it is addressed with error bounds, and there's a lot of error bounds in the literature. Now, the error bounds themselves are not important. What's important is what they tell you about the behavior of methods. Some error bounds are more detailed than others, but they capture fine details of the method that you don't have time to observe, you don't have opportunity to observe, and you can't really understand. The bounds I'm going to give you are among the earliest ones, perhaps the earliest ones, and the simplest ones. And they are important because they mirror practical behavior. And here's the first bound. It has to do with approximate non-optimistic policy iteration. So we generate a sequence of policies with policy evaluation and with policy improvement. Let's assume that the policy evaluation error is within delta, okay? In other words, you have the base policy mu k at a given iteration, and you consider the evaluation of that base policy, which you use in one-step look ahead. Now, this may not be the same because of neural network approximations, because imperfect simulation, and so on. We don't examine the source of the error, but we assume that the error is within delta, maximized across states. We also assume a policy improvement error. So this is the error in the policy evaluation operation. In the policy improvement error, we minimize this expression. Suppose now that we obtain the new policy, not by exact minimization, but by minimization that's accurate within epsilon across states. So there are two approximation errors here. Delta quantifies the error in policy evaluation. Epsilon quantifies the errors in policy improvement. And what you can show is an error bound like this. And now I'm going to explain this and what it means as a practical matter. What I have here is an oversimplified picture that's projected on a two-dimensional plane. We look at J star, we represent it by a single number. So let J star is this level here, the optimal cost. And these are the costs that are generated, that correspond to the different policies generated. This is the initial policy. Of course, it is worse than the optimal, right? And this is the degree of suboptimality. Then we obtain at iteration 1 a policy mu1, and its cost is this one here. At iteration 2, a policy mu2, this cost, and so on. So we obtain a sequence of costs. We are not guaranteed that this sequence is going to be monotonically converging to J star. This is only true for exact policy iteration, not for approximate policy iteration with these errors. However, what we can prove is the following, that asymptotically, as the number of iterations increases, this is k, the number of iterations, then you are going to come within a zone, an error zone of the optimal, and you're going to stay there. And the width of that zone, uniformly for all states, is given by this expression. Is proportional to epsilon, is proportional to delta. and it's inversely proportional to 1 minus alpha squared, okay? Alpha, remember, is the discount factor, less than 1, but sometimes pretty close to 1. So this denominator can be killing you, okay? Can be a very, very, can make the bound very large. Now, this is what the theory says. And in practice, this error bound is pessimistic. Usually the error is smaller than this. However, there are examples where this error bound has been shown to be tight, exact. So this is a worst case bound that can be that is attained. What else can we say here? There is this oscillation, and how do you know which one of these policies you're going to use? Use this one or use that one? That's a dilemma. The reason is that, yes, you can evaluate a particular policy for a single state or for a small number of states, and you can compare different policies and see how they compare with each other in terms of cost. On the other hand, this is for a single state, and this policy may be worse for one state, but it may be better than other states. So it's not very easy to select a policy out of this sequence that's generated to use as your final policy. You have to do quite a bit of experimentation afterwards. So that's one point to keep in mind. Why is this bound important? After all, we don't know epsilon and we don't know delta. So we can't use as a quantitative measure of the performance of our approximation scheme. This number here is not important in its magnitude. What's important is that there is such a bound. In other words, this says that this policy iteration algorithm is stable in the sense that it eventually stabilizes within some finite error. It doesn't go off to infinity like the fitted value iteration does. The other thing that's important about this bound is that it mirrors practical behavior. In practice, approximate policy iteration works like this. You get typically monotonic improvement for the first few iterations. Usually the first improvement is the biggest one, which corresponds to rollout. And then you get oscillations eventually. A small size oscillations or not so small size oscillation, and different kind of oscillation for different states. So this error bound reflects practical behavior and gives you just about all the insight you're going to obtain from error bounds. It says it's proportional to epsilon, proportional to delta, and inversely proportional to 1 minus alpha squared. Are there any questions here? Okay, here's an improvement to this error bound. Suppose that you use approximate policy iteration, but the policies somehow converge so that the mu k's are not oscillating back and forth, but rather they go to some policy and then they stop there or they approach some policy. Then there's a better error bound. And this error bound involves a 1 minus alpha factor in the denominator less. Whereas before we had square here we have only to the first power. And given that alpha is pretty close to 1, it's a significant improvement. And so if you can have the generated policy to converge, then you obtain monotonic decrease to something that's within this error zone. On the other hand, typically, you have oscillations in approximate policy iteration. Certainly this is true with alpha 0, certainly it's true with backgammon. In most cases, unless you use a particular type of method for policy evaluation, which has some properties, then you're not guaranteed convergence. On the other hand, there are some methods where convergence of policies is guaranteed. And one of them is using aggregation. I mentioned this, I mentioned several times aggregation. I promise I'll say something more before the course is over. But as a preview, if you use aggregation for policy evaluation, then you get this better bound and this better behavior. Now, there are other policy iteration methods, multi-step, optimistic, and so on. It's almost all of them are like this, okay? They just differ by the error zone, and they differ by particularities, how violent the oscillations are, and things like that. So that's what you should be looking for in approximate policy iteration as a check as to whether you're doing the right thing. You should be getting monotonic improvement in the beginning, typically, and oscillation afterwards. Interestingly, when the field is still young, people were getting these oscillations, but they were not reporting them because they thought that their method is wrong, that their software has bugs. But eventually, it became understood that oscillations were the norm and not the exception, or the result of a method flaw. Questions? Okay, I'm going to give you one more error bound, which is more complicated. This does not have to do with policy iteration. It has to do with rollout, truncated rollout with multi-step look ahead. It's one of our favorite algorithms, and it has an error bound that says something about how it works. So let's consider truncated rollout with L step look ahead minimization, followed by a rollout with a base policy for M steps, and then followed by terminal cost function approximation J tilde. And we have this result here. How does the rollout policy compare with the optimal and also with the base policy? We have this error bound. Okay, so what does the right-hand side here, what does the left-hand side here involve? Okay, this denotes norm, the maximum norm. So this is the maximum difference between J mu tildes of X and J stars of X, maximum over all states. The maximum norm is a legitimate measure of error between the performance of the rollout policy and the optimum. And this satisfies the following inequality that involves L, the number of steps for look ahead. The more look ahead you have, the better off you are in terms of this bound. It involves M, the number of steps that you use for rollout with the policy. The distance between the cost function approximation and the cost of the base policy. The distance between the cost of the base policy and the optimum. All of this play a role in this bound here. Of course, if you were not to use cost function approximation, terminal cost function approximation, this term would go to 0 here. And if you're lucky enough to get a base policy that's pretty close to optimal, then this would also go to, it will be near 0. Okay, so this is error bound between rollout policy and optimal policy. And there is also a cost improvement bound. Given the base policy, how much can you improve it, okay? This gives the cost of the rollout policy compared with the cost of the base policy, and the error bound involves M, the number of steps, and the distance between the terminal cost approximation and J mu. In particular, if you use exact rollout, where J tilde is equal to J mu, then you get the cost improvement inequality, the standard cost improvement inequality, the basic property of the rollout procedure. So again, these bounds are not very useful in practice, because how can you calculate this term? Surely you can't calculate this term because you need to know J star. You can't bound it, you can't calculate it. Similarly, you can't calculate these terms here. So that these are not quantitative bounds, but they are qualitative bounds in the sense that they tell you what you can expect from the method that you implement as you change various parameters of the method. As you change L, the more the look ahead is, the better off you're going to be. The longer the rollout is going to be, the better off you're going to be, according to this bound. For large values of M, this may not quite be true. So one should not take these bounds too literally. One should check them against practice. But I think that the fact that they enter, L and M enter these calculations is helpful. Finally, as you would expect, if the base policy is closer to the optimal and this error is small, then you should be getting better performance from the rollout policy. And as the terminal cost approximation is close to J mu, you'll be getting close to exact rollout, and you will be getting cost improvement as well as a better bound from J star. None of these bounds, these bounds are, some of these bounds have sophisticated proofs, but what I like about these bounds, and I recommend to you that you take a look at the proofs, is that the proofs are insightful. They give you some idea about why the methods work just by looking at the mathematics. And I think that's important. And also the line of proof that I gave earlier for policy iteration, this line of proof comes up again and again in various convergence proofs of policy iteration variance, and also in various bounds for variance of policy iteration or rollout. So we covered a lot of ground in terms of the theory of these methods. Like I said, there's a lot of interesting mathematics, a lot of interesting insight to be obtained from the mathematics. And I hope that you will take the time to look at them as you also try to implement useful methods. So are there any questions? Okay, so this was the 9th lecture. We're going to do 3 more lectures plus a review lecture at the end, where I'm going to tell you what I told you, basically. In the next lecture, we're going to use a video that's posted on the internet to talk about multi-agent rollout and policy iteration in a distributed setting. Not only multiple agents, but also partitioning of the state space and the use of parallel computation. And I'm going to discuss 2 case studies that I already shown some videos. One is the POMDP single robot repair problem, and but with state partitioning to deal with a large dimension of the problem, the large number of states. And the other is going to be the multi-agent repair problem that I showed 2 lectures ago. And we're going to go into policy iteration. I think I showed you how rollout works for that for that problem. Now we're going to discuss also about policy iteration. So all of this is recent stuff. There are research papers that are describe these works, and they are posted. The research papers are posted on my website. And there's also videos, one from a lecture that I gave in UCLA last February that's posted at my website. So you may want to watch those videos before you come to lecture. So that's the next lecture. And the lecture after that, that would be lecture 11. It's going to be on approximation in policy space and policy gradient type of methods. We're not going to discuss these in great length, but I want to give at least one lecture on it. These methods are very popular, and people use them a lot, and I'd like to describe them to you. And lecture 12, as of now, is planned to be on aggregation. So multi-agent distributed next lecture, policy gradients lecture after that, and then aggregation after that, and then a review lecture at the end. And that's the plan for the rest of the course. We don't have any homework, but I'm sure you have your hands busy with your projects. I've heard from several of you about your projects. Some of you are doing very, very exciting things, and I was very pleased to see them. And I look forward to continuing interactions with you about the term projects and also to see the results of the final efforts. Are there any questions? Okay, guys, so we'll meet next week.